7, and chapter 7 is about alkyl halides and its reactions. Of course, as usual, we will discuss the following aspects: the nomenclature of alkyl halides, the synthesis or preparation of alkyl halides, and the reactions of alkyl halides. Now, regarding the nomenclature of alkyl halides, first let's just remind you with the general classification of these alkyl halides. It depends on where the halogen is attached to the alkyl groups. If it is directly attached to sp3 hybridized carbon, then we will call it, or we will name it, alkyl halides. If it is attached to sp2 hybridized alkene, directly attached to the carbon, which is sp2 hybridized carbon, we will call it vinyl halide, as we have actually classified it in the first chapters, if you remember, in chapter 2 or 3. And finally, if it is attached to a benzene system or benzene ring, we will call it aryl halides. For the nomenclature, as we have also explained before, nothing special actually for the nomenclature of the alkyl halides. The halogen in general, they have no special priority in the nomenclature. Maybe the only priority present actually for the nomenclature of halogens, it's simply when they have, or when we use their alphabetic priority order in case there is no more important priority, as we have explained before. Now, the examples what you have in the slides, in slide number 3, we have, for example, the compound and the names of the compounds. And see in here, we have to start from the right side of the compound. So we just redraw the structure. We'll have 2, 4, 6, 7. So we'll have CH3, CH2, CH2, then we will have CH, CH3, then CH, Br, then CH, CH3, then CH3. As you can see in this example, nothing special here. We don't give any special priority for the halogen for the nomenclature. We just follow the rules, looking for the longest continuous chain of carbon atoms. Then we must start numbering the chain closer to the first branch. As you can see, this applies to the right. So if we start numbering from here, we'll have, regarding the numbering, 1, 2, 3, 4, 5, 6, 7, and then we will simply list the substituents with their numbers, or with their position at the system, or at the alkyl chain. As you will see, we will have the bromo here, we will have it 3, and then of course, as you remember, one rule here, we have to list all substituents based on their alphabetic priority. So we will start with the bromo, so we'll have 3 bromo, then 2,4-dimethyl heptane. So this is just to remind you actually the most important aspect for the nomenclature of alkyl halides. Now, for the reactivity, for the reactions of alkyl halides, in order to understand or to discuss the reactions of the alkyl halides, we need to understand the polarity of the bond, actually the bond which is carbon-halogen bond. So in principle, as you all know, the halogen in general, they are high, or they have higher electronegativity compared to the carbon, and therefore they will carry always a partial negative, and the carbon will carry a partial positive. And of course, logically then, for the reactivity of this functional group, we should expect actually the carbon is simply susceptible to the attack of a nucleophile, because simply this is a partial positive, which means this is electrophile behavior, or it has electrophilic behavior, and therefore it should be susceptible to the attack of a nucleophile. And the nucleophile, as we have explained it before, The nucleophile is any negative ion species or any neutral molecule, but of course it must contain a lone pair. We'll come to this when we'll discuss the reactions of the alkyl halide. Now, for the preparation of the alkyl halides, the synthesis, how we prepare this functional group. We always, we can actually prepare the alkyl halide from different functional groups, as we have also explained before. For example, the first method, it was the reaction by addition reaction of hydrogen halide to alkene, and this addition reaction, which we have discussed or explained in chapter 4, we know that any alkene, when we allow it to react with any HX, where X here can be chlor, brom, or iodine, then there will be addition reaction where we will have hydrogen will add to one carbon, and then the X will add to the another carbon. The most important thing actually to remember is simply this reaction always occur following the Markovnikov addition rule, which means the hydrogen in here should add itself to the carbon, which contains more number of hydrogens, as you can see in the example in the slide. The other reaction, which we have also explained, but this actually reaction applies for the preparation of dihalide. It's simply by addition or halogenation reaction to alkene. So whenever we have alkene, we're allowed to react with, for example, halogen like bromine in presence of CCl4 or in the presence of the solvent CCl4, then the two halogens will add themselves to the two carbons, and thus we'll have dihaloalkane. In here, actually, we have also to remember the stereochemical aspect of this reaction, which means that two halogens, they should add themselves to the two carbons in anti manner. So we will get simply, if we have a cyclic system, we will then definitely we will get the two bromines will be trans to each other again, as you can see it in the example in the slide. The third reaction, which is actually the only reaction possible to react alkane or saturated alkane. In here, we can prepare alkyl halide from saturated alkane by halogenation, and the halogenation here is the use of halogen in the presence of light or heat, as we have also explained before. And as also we have explained before, this reaction is good, is practical, is suitable actually for alkane, in which most of all of the hydrogens are equivalent, in order not to get many products or byproducts actually, as we may get if the hydrogens are non-equivalent. For example, if we have a cyclic system like cyclohexane, cyclopentane, cyclopropane, and so on and so forth, these cyclic systems, all the hydrogens are equivalent, and therefore when we allow it to react, we can control the reaction to react, for example, with halogen in the presence of the light to get monobromination, and thus we may get a good yield of this reaction. But in case, for example, this alkyl for this alkane, it's not equivalent, we may get actually like a mixture of products, which is in organic chemistry is not advisable, it's not recommended, it's not preferred actually. So these are the three methods so far for the preparation of alkyl halides. Other method actually we may prepare alkyl halides from the corresponding alcohol, and in this case all what we need. So for example, if we have RCH2OH, we can allow it to react with hydrogen halide, and with the heat we will get RCH2X plus H2O, and this here actually, this reaction is affected by the nature of the alcohol we are talking about. So as you can see in the slide, generally speaking, tertiary alcohol are more reactive than secondary, more than primary alcohol than methyl alcohol, which is the methanol in this case. In this, therefore, what does that mean? Most likely this method for the preparation is suitable, more practical, easy for the preparation of tertiary alkyl halides. So this method most likely good for the preparation of tertiary alkyl halide. If we need to prepare, for example, primary or secondary or methyl alkyl halide, then it's better actually to use the next method, which we have it actually as method E in the slides, which is either to use the phosphorus tribromide or to use the thionyl chloride if in case we need to prepare alkyl chloride. So for example, if we want to convert ethanol to bromoethane, so what we need here is to react it with phosphorus tribromide. We will achieve that. If we want to convert, for example, cyclohexanol into chlorocyclohexane, it's better actually to use thionyl chloride in this case, and we can achieve so. So in principle, depends on the nature of the alkyl halide which we are going to synthesize. If it is tertiary, prefer to use the method E, which is the reaction of alcohol with HX directly. If it is primary or secondary or a methyl, then it's better actually to use either the phosphorus tribromide for bromination or thionyl chloride for chlorination of the alcohols. Now let's talk about reactions. What are the reactions which alkyl halides undergo? In principle, as we have when we explain the reactivity of the alkyl halide, as you can see it in the board in here, you can see it very clearly as that the carbon here has an electrophilic behavior, and thus it will always react with nucleophile. This reaction, we call it nucleophilic substitution reaction. What does that mean? That the nucleophile will attack the carbon, will displace or replace the halogen, and thus we will get to the nucleophile. Now, there are two mechanisms actually which explain this reaction, as you can see it in the slide here, in the slide of the section 7.4. There are the Sn2 or Sn1 reaction mechanisms. In both of the reactions, we are going to get the nucleophile displacing the halogen. So this is always what we're going to get. So if we have a nucleophile attacking the alkyl halides, the nucleophile will displace or replace the halogen, and therefore we will end up of a nucleophile attached to this carbon, and then we will have the halogen as a leaving group. So the halogen in here, we call it leaving group, and the nucleophile here, as we will explain later on, it's, or as you all know, it's any negatively charged ion or neutral compound which contains a lone pair, and this is the alkyl halide in here. So we have actually two mechanisms which explain this reaction. But before talking about these mechanisms, let's first discuss what's the nature of the product actually if we have the nucleophiles are different. You know, in principle, the nucleophile either to be negatively charged or neutral. So we will just make it like this way. So if it is negatively charged, which means any negative ion reacting with any alkyl halides, or a neutral reacting with any alkyl halide. In both cases, what we are going to get our nucleophile. As you can see, it is nucleophilic substitution reaction. The nucleophile will substitute the halogen, and the halogen will be leaving the reaction. You follow me? But in the first reaction here, when the nucleophile is negatively charged ion, directly we are going to get our nucleophile. That's it. In this case here, we are going to get the product directly. But in case when we have the nucleophile is a neutral, first we are going to get as intermediate product, we are going to get R nucleophile and then H, and of course, since this is a neutral compound, it will carry, the product will carry a plus. I'm sorry, it's not a partial, it's a formal plus. Then finally, this compound will lose a hydrogen or a proton in this case, and then we are going to get finally the same compound. So it doesn't matter if we use a nucleophile which is neutral, or if we use a nucleophile which is negatively charged. Both cases we are going to get the same product. But of course, as you all should expect, actually, when we use a nucleophile which is negatively charged, will definitely be faster in reaction compared to the neutral one, because simply it contains a higher electron density, and thus it should be expected to be faster in reactivity. So these are actually the difference between the nucleophiles. Please, if you have any question before going to explain the detailed mechanism of Sn1 and Sn2, if you have any question, let me know. If is there any question? Is there any question? I need to see any response in here. Either yes or no. Everything is clear? Wonderful. All right. So if there is any question, please never hesitate to just ask your question right away. I always look at the chat here, and then I can see it. Now let's explain the characteristics of the first mechanism. It's what we call it the Sn2 reaction mechanism. It's in there actually, so no need to redraw it, but I'm just going to show it to you by modeling here, and especially focus on the inversion of configuration which is associated with this type of reaction. Of course, we're talking about reaction of nucleophile with alkyl halides, which means the alkyl halides, as we have explained it before, it's a carbon connected to sp3 hybridized carbon, and sp3 hybridized carbon will be definitely connected to 4 bonds. Now, imagine, for example, the halogen in here for the alkyl halide is the red color. In the Sn2 mechanism, what we are discussing now, which is the Sn2 mechanism, in the Sn2 mechanism, the nucleophile will attack the carbon from the back side, as you can see it in here. The nucleophile will attack the carbon from the back side, and then this will leave, and then we will get the nucleophile connected to the carbon. In transition state, you can simply think of the transition state like this. Remember, the nucleophile, the halogen is the red color. So this red color will be by 180 degrees with the nucleophile, and the other 3 atoms will be like this. It's like actually the bipyramidal structure, as you can see it in here. But the most important thing, you remember that the nucleophile will attack from the back side of the carbon to the halogen. So these will be always opposite in the transition state. And finally, of course, this will break up, this bond will break up, and then this carbon will change its hybridization to the sp3, and then we will get the final product. So in principle, this is actually the characteristic of the Sn2 reaction mechanisms. The most important criteria of the Sn2 reaction mechanism is that all bond breaking and making occurs at the same time, which means that's actually why we can imagine of the transition state like this structure, but because simply this nucleophile started to make a bond with the carbon, and at the same time the carbon halogen bonds start to break up, because simply, as you all know, the maximum number of bonds which carbon can make is 4, and therefore the carbon is highly energetic actually in this transition state. It cannot be connected to 5 bonds. Therefore, the lifetime of this transition state is very, very short. The most important thing, which is depending on this transition, is that always if we started up with a carbon which is chiral carbon or stereocentral carbon, in this case, if this R compound as alkyl halide, what we are going to get, the mirror image of this. There will be inversion of configuration. If this is R, we are going to get S, and vice versa is true. In other words, if this is S, we are going to get R. So remember this, Sn2 reaction mechanism always occurs with inversion of configuration. This is a very important aspect regarding the Sn2 reaction mechanism. Is that clear? Any question about the Sn2 and specifically its characteristic or its character of having inversion of configuration of the compound? All right, perfect. Any question? Wonderful. So now if we have, of course, alkyl halides are different by the nature of the carbon which is attached to the halogen. Of course, we can classify it in general as tertiary alkyl halide, secondary alkyl halide, primary alkyl halide, and so on and so forth. So which alkyl halide will be faster in reaction in this type of reaction, in this Sn2 type of reaction? Actually, as you can see it in your slide, always the methyl, of course, the methyl alkyl halide is very higher in reactivity compared to the primary alkyl halide, and the primary alkyl halide is higher in reactivity compared to the secondary alkyl halide, and this will be higher in reactivity compared to the tertiary alkyl halide. In principle, this will never, the tertiary alkyl halide will never undergo Sn2 reaction mechanism, because simply due to the steric hindrance. In this here, these 3 hydrogens here, for example, again here, this is an alkyl halide, and we need, for the Sn2 reaction mechanism to take place, we need the nucleophile to attack from the backside. Now, if these are hydrogens, for example, the methyl alkyl halide, that would be wonderful, because there is enough space in here from the backside for this nucleophile to attack, and thus then the halogen will leave. But if these groups are R groups, in other words, they are carbon connected to other hydrogens and so on and so forth, you can imagine, or you should imagine, that these groups like balls here, therefore there will be like steric hindrance here. These will repel actually the attack of the nucleophile, therefore the rate of reaction will be very much slow as the number of R groups here increases. And that's why we see here the tertiary alkyl halides will never undergo Sn2 reaction mechanism. And as the number of R groups becoming less and less, the reaction rate will be faster and higher. This is actually, or these are the most important aspect and characteristics of the Sn2 reaction mechanism. Now regarding the halogen, now which halogen is better or better leaving group in principle? The rule here actually is always, as the basicity of the leaving group becoming less, the leaving group becoming better leaving group, or in other words, it will leave faster and the reaction will become faster. Now if we compare the basicity of the halogens in principle, if for example, if we compare the iodine I minus compared to Br minus compared to Cl minus compared to F minus, then we will find that the I minus is the best leaving group, while the Br is better than chlor, and this is better from the F minus. And this is very simple. Leaving group always is the least basic one. This is always depending on the basicity. So in order to have better leaving group, or the group to leave easy from the carbon, then it should have the characteristic of being a weak base. So, and of course, the basicity, of course, if you have to remember, it's always connected to the conjugate acid. So HI is the way stronger acid compared to HBr, compared to HCl, compared to HF. Because, of course, as you all know, the strong conjugate acid will definitely, strong acid will produce a conjugate, a very weak conjugate base. So the leaving group ability always depends on the basicity. As the basicity of the leaving group becoming less, then the leaving group ability will be better. The two other leaving groups actually which we have, the other or superpower leaving group actually, which is we have a leaving group called the tosylate, and the tosylate here coming from the tosyl acid or toluene sulfonic, para-toluene sulfonic acid. And here, as you can see, this here we consider it as a very powerful leaving group. This is very powerful leaving group due to the very low basicity. This is very low basicity. Anyone knows why this tosyl group has a very low basicity? Anyone has any suggestion why this leaving group has very low basicity? Any suggestion? If you have any suggestion, please write down. No volunteers to write down? Any suggestion? Alright. Actually, exactly Rashid. That's absolutely the only reason for that. Is that actually more stable, the most stable. But why more stable, Rashid? Why do you think this is more stable? Remember about the stability of any charge system. What are the most important factors which determine the stability of any charge system? No, Al-Harith, no. It's actually due to the stability, it's delocalization. Right, okay. Let me just reformulate it. This is very powerful leaving group due to the stability. It's very stable base. Which means, or why this is very stable, due to the presence of resonance structure. Because if you try here, if you look carefully, you can see that we may draw different resonance structure of this leaving group. So here, for example, the lone pair here, the negative charge can make a double bond between oxygen and sulfur. This goes up, and therefore we are going to get O minus, the bond O, and then the bond O. And then this can continue. This can go here, and this goes there, and therefore we may draw three resonance structures of this compound, and therefore that's why actually this is more stable or very the negative charge is highly delocalized. Exactly. Generally speaking, as we said, the negative charge or any charge system will be more stable if the charge is delocalized. The delocalization here actually is due to the resonance structures. Now, the same applies here. When you compare, for example, iodine, for example, I minus with Br minus with Cl minus with F minus. Why here? This is the most stable base here. Why the negative charge at the iodine, when it's connected to iodine, is highly stable one? Why? Because of delocalization, definitely. Now, how the delocalization? Because iodine is very big size. So in this case, the negative charge will be delocalizing over very high charge, and then therefore I minus, which has very higher size compared to Br minus, will be more stable compared to Br minus, compared to Cl minus, F minus, and so on and so forth. That's the reason behind the nature of the leaving group and how it become better leaving group or bad leaving group. And therefore, for example, bases like RO minus, for example, or NH2 minus, for example, these are very bad leaving groups. Why they are very bad leaving groups? Because simply the negative charge will be highly localized on oxygen atom or nitrogen atom, and therefore it is almost like impossible to displace these functional groups in under normal conditions. In order to make, for example, to force these to behave as leaving groups, so we will definitely need to have vigorous conditions, which is simply beyond the scope of this course. So in principle, we are always going to discuss the leaving groups like halogens or the tosyl, which are very good leaving groups. Now, beside Sn2, we do have, or before actually going to the Sn1 reaction or mechanism, is there any question about Sn2 aspects before discussing the Sn1 reaction mechanism? Any question about Sn2 reaction mechanism? Perfect, thank you. All right, so let's now discuss the other mechanism, which can explain the nucleophilic substitution reaction, which we call it Sn1 reaction mechanism. In the Sn1 reaction mechanism, it is a two-step reaction mechanism. In other words, we are going to get the product, we are going to get the nucleophile displacing the leaving group, but in two-step reaction mechanism. In other words, in here, as you can see, in the Sn2, everything, bond breaking and bond making happens at the same time. But in the Sn1, first of all, the leaving group here will leave, the bond between the carbon and the halogen will break up, and therefore this carbon was tetrahedral. It has a tetrahedral structure, it has sp3 hybridization. When the bond here break up, then that means the carbon will become partially formally positive charge, and therefore the hybridization of the charge here will be sp2 hybridization, and the sp2 will have a structure or a geometry of planar triangular, and therefore there will be like the bonds like this here, like in the same plane of my hand. Do you follow me? Now, and then the nucleophile will attack, simply because the nucleophile is negatively charged, the carbon is positively charged. So, but in this case, as you can, if you remember the bonding and the geometry of the bonding, the carbon in here will be connected to a p orbital, which is perpendicular to the plane of the bonds. So the p orbital always has two loops. One is above the plane, one below the plane. Now, therefore, the nucleophile will attack. It can attack from above the plane, and therefore this umbrella will go down, or it may attack from below the plane, and therefore this umbrella goes up. Now, each one will be like a configuration, and therefore always Sn1 reaction mechanism occurs with of what we call it racemization. In other words, if this alkyl halide was chiral compound, it was, for example, R, the product will be always racemic mixture, which means RS. It will be both mixtures, or a mixture of both compounds in this case. So the most important criteria which determines alkyl halide to undergo, okay, exactly Al-Harith, what do you mean by which part actually I should repeat? Alright, again, Sn1 reaction mechanism, I'm going to repeat the whole issue. Sn1 reaction mechanism, as I said, it always occurs in two steps. The first step, the bond between the carbon and the halogen first will break up. You follow me? Now, of course, if you remember, this is alkyl halide, this is sp3 hybridized. The geometry will be tetrahedral, isn't it? Right? Interact Harith. Yes, right. When this bond break up, then that means this carbon become carbocation. And the carbocation here always has sp2 hybridization. So carbon attached to 3 bonds, this carbon and carrying a plus, this will be sp2 hybridized carbon. In this case here, the sp2 hybridized carbon, it's like this actually. It will be, the geometry of the sp2 will be for example, triangular planar like this, right? Now this is sp2 hybridization or hybridized carbon. Now therefore, when the nucleophile attacks here, it has 2 positions to attack, or 2 possibilities to attack. Either it attacks from the above the plane, therefore of course the carbon will change its configuration or its hybridization into sp3, therefore these 3 bonds will go this attacking from above, that means these must go down. Or vice versa. The nucleophile can attack from downward, and therefore the umbrella which can be made by the 3 atoms will be making from the other side. In other words, both possibilities are there, therefore always if we start with R, alkyl halide, what we will end up, and this undergoes or underwent Sn1, what we will always get R and S, which means we will have a racemic mixture of both. Or if we start with S, doesn't matter, we are always going to get R and S mixture, racemic mixture in this case. Is that clear, Harith, and everyone is there? Al-Harith, is it clear now? Is there anything? Alright, perfect. So as you can see here, the most important criteria which determines the Sn1 actually is the stability of the leaving group. The stability of the carbocation. Because remember, forming a positive charge or forming a charge in principle in nature, this is not a stable issue, and therefore we need always, whenever we have factors making the stability of the intermediate better, then therefore it will make the reaction faster. So since this reaction involves the formation of a carbocation, so the more stable carbocation, the faster the reaction is. And you can see in the slide what we have actually explained before, which are when we compare primary to secondary to tertiary carbocation, as we have seen before, the tertiary will be higher in stability compared to the secondary compared to the primary. So this is the tertiary carbocation, this is secondary carbocation, this is primary carbocation. and therefore the primary carbocation most likely will never undergo Sn1 reaction mechanism, because the primary alkyl halide will form primary carbocation, which is then will be highly unstable carbocation. Therefore, in the tertiary alkyl halide, which is actually will form tertiary carbocation, always preferred in Sn1 reaction, but primary alkyl halide and methyl alkyl halide will never undergo Sn1 reaction mechanism. Is that clear, guys? So these are actually the factors affecting which mechanism the alkyl halide will undergo when it reacts with the nucleophile. Will it undergo Sn1 or Sn2? As we will see, of course, in the last slide, it will be like a summary of everything, because there is another reaction which we need also to discuss and address, what we call it, the elimination reaction, which we are going to discuss it now. Again, here, this is the stereochemistry in the slide. You can see it here very clearly. It's drawn there. So in principle, the stereochemistry of Sn1 reaction always occurs with racemization. So regardless of the stereochemistry of the alkyl halide we started up, if it undergo Sn1, it will definitely produce racemic mixture of both compounds. Now, whenever we have, so far so good, guys, is there any question about the substitution reaction with both mechanisms, Sn1, Sn2? If there is any question, please let me know. Otherwise, we simply go to the last reaction in this lecture, which is elimination reaction. All right, perfect. Wonderful. Let's talk about elimination reaction. This is always a competition reaction to nucleophilic substitution reaction. So in this case, whenever there is a possibility for nucleophilic substitution reaction, there is always possibility for elimination reaction. Let me remind you with the elimination reaction. What's the meaning of elimination reaction? It is simply a big molecule will eliminate part of it. It will be simply changed into two products. Do you follow me? In other words, as you can see here, whenever we have alkyl halide, there are two possibilities when it reacts with nucleophiles. Whenever we have alkyl halide, RCH, for example, H, then CH2X, with the nucleophile. Either the nucleophile, if the nucleophile attacks this carbon, which is directly attached to the halogen, then we are going to get the product, which is nucleophilic substitution reaction. I'm sorry, I just made it big structure. Let me just make it this way. RCH H CH2X, then with a nucleophile. So there are two possibilities. If the nucleophile directly attack or simply replace the halogen directly, then we are going to get nucleophilic substitution reaction, RCH, then CH2 nucleophile. This is called nucleophilic substitution. And this can go or undergo through Sn1 or Sn2, depends on the nature of the alkyl halide. This is what we have explained so far. You follow me? But there is another possibility, and the other possibility is that this nucleophile here, it may behave as base here. The nucleophile, because simply any nucleophile is also is the same thing as behavior as a base. Any nucleophile is a base, and any base is a nucleophile. It's the same meaning. But sometimes there's just slight difference actually in their behavior, in their nature. If you wish, we can explain it. But let me just finish this. What does that mean? In this case, the nucleophile here can simply take this hydrogen, because what's the basicity behavior? The basicity behavior is that something abstract the hydrogen, the H as H+. In this case here, you see this hydrogen which is at the beta carbon to the carbon connected to the halogen. The carbon connected to the halogen, let's assume it is alpha. The next carbon will be the beta. If we have a hydrogen at this carbon, then this nucleophile can take the hydrogen, and the bond here, or the bond or the pair of electrons which is between this carbon and hydrogen, will be used to make a double bond between the two carbons, and therefore this can leave away, and therefore we are going to get elimination product, RCH double bond CH2 plus HX. طبعا the HX here, we are going in the elimination reaction, we will get HX as another product or as inorganic product. Since we have a halogen X at one carbon, then definitely we need another hydrogen from the adjacent carbon. So always this is the elimination, how it occurs and where it occurs. Do you follow me? So always we need halogen from one carbon and hydrogen from another carbon in order for the elimination to take place. So this reaction always there. This reaction always possible, and we will always consider that, or we'll take this into consideration. So this is called elimination product or elimination reaction. We are not going actually to discuss too much or to highlight too much about the mechanism of this reaction, and this will be actually E1 or E2 mechanism. Just to know that this reaction will be either E1 or E2 reaction mechanism. I'm afraid actually the battery of my mobile phone will go down at any time, and therefore I'm just going to stop now. I'm going to stop for today. We can quickly or take it like 10 minutes on Tuesday just to continue this lecture, because unfortunately the battery of my mobile phone is going down very fast, and we may stop at any minute. Alright guys, we're going inshallah to continue our lecture on Tuesday. Alright, any quick question before leaving? Thank you all for your attendance, and inshallah see you on Tuesday. Stay safe. يعطيكم العافية. السلام عليكم.